Hello, am I audible? Hello, am I audible? Beg your pardon, there was some disruptions with the Wi-Fi internet connection here. That's why I have to move to my mobile phone. So I'll not be able to use camera for the rest of this class, but my voice will be actively present during the meeting. And I apologize for this inconvenience. We can start the meeting as soon as possible. Uh, Hello, am I audible? There was a brief disruption in Wi-Fi. That's why I couldn't connect with my video on my system. So briefly, I had given an introduction in a mobile phone and the reason for the current change in the way in which I will be presenting to them. Is the screen visible right now? Hello, am I audible? Is my sound coming to your side?
Hello, sir. Are you saying anything? Actually, it's not visible. Anything?
Am I audible? Am I audible? Am I audible?
Yes, sir. Now it's audible. Sir, are you presenting anything? Actually,
Hello?
I'm not
Am I
able to.
audible?
Yes, sir. Hello.
Yeah. Am I audible, right?
Yes, sir. Now it's audible.
There was a brief disruption in Wi-Fi, and today I didn't bring my system, so I will not be showing my face, but the voice will be continuously present throughout the meeting presentation.
Okay, sir. So the class is it postponed or are you working on it?
Yeah. Within a couple of minutes, I'll start. Is my screen visible?
Yes, sir. Now it's visible.
Okay, correct. We can continue. So sorry for the brief disruption at the beginning. Uh, Welcome to the 10th week tutorial session of the NPTEL course, Principles of Hydraulic Machines and System Design. My name is Ananthakrishnan. I'm a PMRF scholar. I do this problem solving session as part of my PMRF TA duty. I'm a Ph.D. candidate from Department of Mechanical Engineering, IIT Delhi. In this week, without wasting much time, we can go to the topics. The main topics of discussion that we have seen this week were the positive displacement pump and the air chamber associated, the similarity and dimensional analysis, Buckingham's pi theorem, and specific speed. So, in this week's tutorial session, we'll say a few multiple choice questions and numerical answer NAT type questions based on these lecture contents which were uploaded in NPTEL websites. We can go to the question straight away. In the first question, an air vessel in the delivery side of a reciprocating pump maintains steady discharge output, enables suction head to be increased, enables the pump to run at a higher speed, both A and C. The first question. Am I audible? Uh, the questions states that an air vessel in the delivery side of a reciprocating pump is used to maintain steady discharge output, enables suction head to be increased, enables the pump to run at a higher speed, both on both A and C. So which out of the four options is the right option? What is the use of the air vessel in the delivery side of the reciprocating pump? Am I audible?
Yes, sir, you are audible.
Okay.
So
Right.
to reduce the length of the suction pipe,
Out of the four options, the answer to this problem is it maintains a steady discharge output. It doesn't have any impact on the suction head, and it doesn't have any impact on the speed at which the system runs. What it does, the delivery side of a reciprocating pump air vessel, it smoothens out the oscillations in the pressure and associated the jerk in the flow rates. So this delivery side air vessel can be drawn separately. Air on top of it. So what happens is that the water which is pumped out of the reciprocating pump comes out, and a portion of this goes to the air delivery side air vessel, and then compresses the air above the water column. So this additional energy will be stored as the enthalpy change or the change in energy of this air column above the water. So what it happens is that during the acceleration, so if you consider the speed versus stroke diagram, consider the pressure versus stroke length diagram or the equivalent volume of the stroke diagram. Pressure versus the volume. So in the delivery side, if you consider this to be the our the expected value or the average value of the pressure at which the fluid should be delivered or water should be delivered, the exact pressure which will be formed due to the inertial effects and as well as the frictional effect will be a bit more different. So what happens is that initially during the return, during the return stroke, there will be an acceleration. There was an issue with this writing part. So this is the return stroke. So initially the piston will be accelerating. So during the accelerating uh, time, there will be an extra. If this is moving this direction, the inertial forces will be acting on this direction, and as a result, the pressure which is being developed by the pressure, the actual pressure which is being developed by the pump will be very less. To compensate that, the piston increases the pressure inside the cylinder, and because of that, the initial pressure will be slightly higher than the average pressure which should have been present at the time of if there were no inertial effects. And similarly, at the end, there will be a decelerating effect. In order to deliver a constant pressure, the pressure inside the cylinder reduces. And this will be the actual pressure versus V diagram for the discharge side. And correspondingly, there will be additional frictional effect also, but we haven't taken into consideration regarding the frictional effect. But in order to compensate the inertial effect, what happens is that the pressure at which the fluid will be delivered will be varying throughout rather than the average value which you require. So to compensate for that, to smoothen out this pressure difference and corresponding discharge rate, we use an air vessel in the discharge side. So what it does is that it maintains a steady discharge output by smoothing out the oscillations in pressure as well as the jerk in the flow rate. Uh, So the pressure which is being delivered will not be a constant. So when the pressure is high, a portion of the pressure when the pressure is higher than what we require, uh, so delivering the fluid to a required height, the portion of a portion of the fluid which is being delivered out of the pump will be going and will be compressing the air above the water column, and this extra energy will be stored as the enthalpy or the change in energy of the fluid of the air. So at the end of the delivery stroke, the actual pressure inside the pump will be very much less than the pressure value which we require. And because of that, the delivery pressure will be low, and the extra energy which is being stored in the buffer tank or the air column will be used to push the liquid which is coming out of the uh, delivery side of the piston at a lower pressure, and this additional pressure will be acting on this additional pressure of the air, energy stored in the air will be acting on the fluid, and because of that it will be delivered to the required height. And what it does is that this kind of act like a flywheel that we have learned in the undergraduate courses. So it stores the extra bit of energy in the air column, and that will be delivered when the pressure will be less, and smoothing out the whole process. So the answer to this problem is that it maintains a steady discharge output to avoid the kind of jerk that is expected of this kind of reciprocating systems. Uh, any doubts regarding this problem? Can we move to the next problem? Am I audible? Hello? Hello? Am I audible? Hello? Am I audible? We can move to the next problem. The next question is also regarding the air vessels in the reciprocating pump. The actual usage of the air vessel are which of the following four options are the represent the actual usage of air vessels in the reciprocating pump. It smoothens the flow, it avoids cavitation at the inlet, it reduces acceleration to a minimum, all of the above. So the answer to this problem is all of the above. So air vessels are used, as we have seen in the previous cases, it is used to smoothen the flow.
Yes, sir, you're audible, but now it's not hearing anything. Just before it was audible.
Yeah. I'm audible right now.
Yes, sir. But
Okay,
sometimes breaking.
okay, fine. Just please bear with me for today because I'm having some issues with network and I forgot to bring my system. So I'm using the system without having a camera on, and I'm using my headphones uh, as a mic, and that is the reason for this poor connectivity and poor sound which is coming from my side.
Sir, I think the record section will have the sound, isn't it?
It should be fine. The second condition is avoid cavitation at the inlet. So basically, what it does is that cavitation occurs when the pressure inside the chamber goes much below the vapor pressure. So by smoothing out the pressure differences, it prevents the pressure from going very much below the vapor pressure. So at the suction side, if you consider suction side, this is the this is the value of the pressure which will be present if there was no inertial effects. But the real case, when the inertial effects come, expected and feel. So when with the advent of inertial pressure, so the actual pressure inside the chamber at the beginning of the cycle, at the beginning of the suction process, will reduce, and there is a chance of the possibility of cavitation. And to prevent this, what if you are using an air vessel at the delivery side, at the suction side, when the pressure inside the chamber is very much lesser than the vapor pressure, the extra energy stored in the suction side air vessel will be applying extra bit of pressure on the incoming air and increases the pressure to reach the expected value of the pressure to overcome the initial effects due to the acceleration. And this acceleration and corresponding reduction in the pressure reduces, and the vapor pressure and the pressure inside the chamber will approach close to the average value it is expected, and it will not go below the vapor pressure. So the second condition is also right. It avoids the cavitation possibility at the inlet of the suction inlet during the suction process. And the reason for this cavitation is a low pressure, and that corresponds to the acceleration. And during the time of acceleration, the low pressure that is expected within the chamber will go even further. So during this initial process, during this initial region of this suction process, the piston is coming inside, and correspondingly a vacuum will be created. And during this acceleration, an opposite inertial force will be acting, and the total available force or the total available pressure inside the chamber, total available gauge pressure which is inside the chamber reduces. To overcome that, the system reduces the overall pressure to increase the reduces the actual overall pressure to increase the gauge pressure, and thereby increasing the pressure difference for the fluid to come inside from the sum which is placed somewhere else. This process, the actual pressure, the absolute pressure inside the pump, the absolute pressure which is present inside the piston cylinder arrangement reduces, and because of that, cavitation arises. So in a way, with the usage of the air vessel, it acts more like a buffer to avoid to reduce the acceleration to a minimum, and thereby preventing the pressure inside the chamber to going below the vapor pressure, and thereby it avoids the cavitation. And another advantage which I have mentioned is it smoothens out the flow rather than intaking fluid at a different flow rate. It almost smoothens out the jerk, and thereby providing a smoothened out water inflow towards the inside the piston cylinder arrangement. So all these options which are given in this question are right. It smoothens the flow, it avoids cavitation at inlet because it reduces the acceleration to minimum, and the answer is D, option D. So if you do not have any questions, we can move to the next program. Question deals with dimensional analysis. That is the second section of the lectures of the previous week. Look into the problem. A dimensionless group which can be formed using variables like density, angular velocity, dynamic viscosity, and diameter will be ABC divided by D square, and these four options are given. Each out of the four options will form a dimensionless group. Basically, dimensionless group means the degree of the independent variables, which independent fundamental variables that will be used for this analysis will be zero. So uh, a combination of A power, you can take the degree or the power to be X or the second quantity B, angular velocity, is power to be V. The viscosity, the dynamic viscosity, is power to be W, and diameter uh, represented by D is power to be S. So these combine together to give the dimensionless group. So the power of the basic fundamental units MLT in this particular case will be zero. Now we represent this A, B, C, D, the quantity given in terms of the basic fundamental units of mass, length, and time. So A is density, so that is can be represented as kilogram per meter cube, or here mass per length cube. And the second quantity is angular velocity. It is radian per second. In the basic fundamental units, it will be represented as sin power minus 1 V. And the third quantity is dynamic viscosity. It can be represented as its unit is kilogram per meter per second, so it could be represented as mass per length unit, time unit minus 1, W, and the last quantity is diameter, its unit is length, power x. So we'll get this equations, three different equations. So what we can see is that as per this analysis, so if you compare between the mass quantities, what will we get is that u plus w equal to 0 when we compare between the right and left hand side. Similarly, for the length, if you compare that, it is minus 3u minus w equal to 0. And if you compare between the times, you could get, I beg your pardon, minus 3u minus w plus x equal to 0. And for the time, what we could see is that it is minus v minus v minus w equal to 0. So by solving these three equations, we can get the values of u, w, u, v, w, and x. The easy option that we can use is that the options are given, and correspondingly we can substitute which out of the following four will be the will be giving you a dimensionless group. So the for example, we take the first option ABC divided by D square. So the units corresponds to ABC divided by D square will be ml power minus 3, t power minus 1, ml power minus 1, t power minus 1 divided by L square. Correspondingly, this will give a unit of m squared into L power minus 2 and t power minus 2. So this doesn't give a dimensionless group. And if you look at the option B, so it gives ABD squared divided by C. That is ml power minus 3, t power minus 1, L squared divided by m power minus 1, L power 1, t power 1. So simplifying this, it will be getting so the unit will be m into L power minus 1 into t power minus 2. So cancelling out the like terms, we will be getting, it will be m power 0, L power 0, t power 0. So this gives a dimensionless group. So the option given in this problem, option B is the right answer, which will give a dimensionless group.
So this type of question, we need to find first the UVW index, and we need to trial and error for all the options.
Yes, yes. As you could see in this problem, it's a three equation and a three equation problem with four variables. So you need to find. You will not be able to solve this. Is not a linear equation, right? You will not be able to solve it. So you have to assume something, and based on that, you will substitute a value of something, and then you will get the other values. So in these type of problems, you can solve like that. There are multiple ways by which we can solve it. In this particular problem, for example, if you give option D, C, the power of C is -1. So the power of C corresponds to V. So if you substitute V equal to -1, you will get the corresponding value of omega W. So it will be coming around, or W will get as 1. So the W is the power of, beg your pardon, if you give the power V equal to, okay, V is the power of B. So correspondingly, if you put V equal to 1, W will be getting it as uh, 1 itself. So W is the power of, missing somewhere. Yeah, I beg your pardon. So in this particular problem, if you put V value equal to 1, V is the power of the t minus 1 second term B. So if you put that particular term as 1, you will get W, W equal to -1. W is the power, W is the power of the third term, ml power -1, t minus 1. So that will be getting us just -1. So that will be coming in the denominator, and correspondingly you can find the other values of u and x from the next set of equations. So in this particular problem, there are four unknowns and three equations, so it can't be solved. So you take value of one and uh, assume it to be a constant, and you using that particular value, you find the other three value, and you will get a set of equations which satisfy this dimensionless case. So this particular problem has been done it like that. Since we have options, we can directly go from the options. Otherwise, you have to go by this method. What happens? V equal to 1, that assume V equal to 1, then you will get W equal to -1, and correspondingly using that you will get U is equal to 1, and using this U and W value, you get the value of X. It will be equal to -3, X is equal to 2. So the dimensionless quantity will be A power 1, second quantity B power 1, C D power -1, and D power 2. So it will be AB D square divided by C. So this is the normal method by which you'll be able to solve. But since the options are given, we have gone for the trial and error method. Any doubts regarding this? So, can we move to the next problem? Audible?
Yes, sir.
Look into the fourth problem. Let's consider that in a fluid machine, the significant parameter for any system are volume flow rate, density, viscosity, work modulus, pressure difference, power consumption, rotation speed, and characteristic dimension. If you are asked to apply Buckingham's pi theorem, what would be the number of independent non-dimensional groups? So in this particular problem, fundamental variables could be taken as MLT. So three fundamental variables you can take. The number of significant parameters are 1, 2, 3, 4, 5, 6, 7, 8 significant variables. Equal to 8. So the number of independent non-dimensional groups equal to significant variables minus fundamental variables. So it will be 8 minus 3, 5. So the answer is none of the above.
So can you explain the significant variable?
Yeah, significant variables are the given variables which are present in the problem. So volume flow rate, density, viscosity, bulk modulus, pressure difference, power consumption, rotational speed, and characteristic dimension. All the eight are significant variables which is present in the question. It is clear. I suppose. Then we can move to the next problem. So read the following statement. Dimensional analysis is used to determine the number of variables involved in a certain phenomenon. The group of repeating variables in dimensional analysis should include all the fundamental units. Buckingham pi theorem stipulates the number of dimensional groups for a given phenomenon. Which of these three are correct? All the three are correct. 1 and 2 are correct. 1 and 3, 2 and 3. Dimensional analysis is not used to determine the number of variables involved in a certain phenomenon because the number of variables are presets that we decide, that the experimentalists decide, which should be used for the further analysis. So dimensional analysis has got nothing to do with deciding the number of variables. What it decides is the group of repeating. Yeah.
Sir, is the fourth option correct one? 2 and 3.
Yes. Right. So one is for this dimensional analysis uh, gives using this Buckingham pi theorem, the dimensional analysis gives the number of dimensional groups for a given phenomenon. That is the right option that we have seen in the previous lecture. The group of repeating variables in dimensional analysis should include all the fundamental units. So the if you consider the repeating units uh, not something which is related to the fundamental units, the fundamental units will be MLT. But the repeating variables should be equal to the number of the fundamental units. So there should be three number of repeating variables, and the repeating variables should contain the number of the repeating variables should contain all these quantities MLT1. So we can't decide three repeating units from the total number of variables which we have preset. We can't take three different variables in such a way that uh, all the three will not be having even a single quantity of either M, L, or T. All the quantities M, L, and T should be present in one form or the other in these variables. Suppose if you take three different quantities, one is density, other one is characteristic dimension, maybe a length, and the other one is velocity. So the density unit is kilogram per meter cube, length is meter, and velocity is meter per second. So in one form or the other, all the three fundamental units of mass, length, or T will be present in these three variables. So we can't take two different repeating variables in such a way that we can't take three different variables in such a way that combined together they will not be having any effect of either of these fundamental units. Suppose if we take the third dimension to be a different form of length, maybe diameter or something. This is right, but if the third unit is diameter, so this characteristic dimension is length. For diameter also length, and this particular unit is kilogram per meter cube or kilogram per meter cube. That is mass into length power minus 3. So there is no presence of time in this particular unit. So we can't take a set of repeating variables in such a way that the effect of uh, at least effect of at least one is not there. So this is a wrong case. So the dimensionless variable should be taken in such a way that the presence of the either of this repeating variable, the presence of the fundamental units must be present in some form or the other in all the three combined together. So option 3 is right, option 2 is right, option 1 is not right. So in this particular problem, question 5, fourth option is the right option.
So the pi variables mean all are independent variable, or only the dimensionless variable.
Dimensionless variable that can be dependent, that can be independent. We can have a relationship between.
So the pi variable means it will be dimensionless. Can you
Yeah,
say like that?
yes, it is dimensional.
Okay.
In several cases, they will be dimensionless, and we can develop a relationship between all the three pi units. So we can write pi1 equal to function of pi2 comma pi3. Like that, we can write.
So we will be converting this other variable which is independent. Uh, I mean, we will be finding out if there are pi variables. Does that mean the one of the four other will be depending on the other one? So I mean, we will be finding out the pi variables and one dependent variable, isn't it? In this theorem.
Exactly, exactly. So that's basically saying, for example, q is the unit, and q is a particular variable. It's a variable that we consider in this analysis. Our repeating variables will be density, length, and velocity. So it will be having ABC different kind of units, and multiplied by q, that should be giving you a dimensionless unit. So ml comma t0. Basically, what we meant to say is that the dimension of uh, this particular unit a comma b comma c will be formed in such a way that it will be inverse of the dimension of the additional variable q. So similarly, if total number of variables are 9, corresponding number of repeating units are 3, we can get, we multiply this with this one independent unit, and correspondingly, one repeating variables, beg your pardon, one variable which is other than the repeating variables and the independent units, or the fundamental unit. So we'll be having 9 minus 3, 6 different variables, and correspondingly, this is the first one. Similarly, second one will be there, 3, 4, 5, and correspondingly, 5, 1, 5, 2, 5, 3, like that. 6 different pi terms can be there. What we can write is that pi1 is a function of other 6 variables. We can since they are dimensionless, we can have some kind of relationship between all the 6.
Okay, sir.
And the various types of similarity, kinematic similarity between model and prototype is a similarity of only shape, both shape and discharge, streamline pattern forces.
So both shape and discharge.
Oh, no, it's kinematic. So shape corresponds to geometric similarity, and so that is wrong. So in kinematic similarity, it's only the velocity will be taken into consideration. That is a streamline pattern. Forces corresponding to dynamic similarity. Velocity.
So, can we see by meaning the dynamic similarity will be considering both shape inside the dynamic, isn't it? So, like
What?
that, I mean, the dynamic similarity means we will be considering the forces. Also, the other two are included in it,
Yes,
isn't it?
yes, 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 yes.
So,
Dynamic
similarly,
similarity.
can we? Okay, similarly, can we say this by meaning the kinematic similarity, both the geometry and the other one included in it? I mean, the option B, like
No,
shape is actually geometry and discharge is actually velocities coming inside it.
but that doesn't give discharge actually. Uh, it doesn't give you the direction of the flow, right? So kinematic similarity will actually give the direction. So velocity is involved. Discharge doesn't give you that, right?
Yes, only the volume flow rate. Okay.
Yeah. Okay. So out of this question, if it was yeah shape and streamline pattern, yes, you could have picked that show or picked that option.
Okay, sir.
So we can move to the next problem. It's a numerical problem. It's given that around 3 meter cube of water per second is lifted to a height of 30 meter with an efficiency of 75% by centrifugal power. Take impeller diameter and rotating speed as 300 mm and 2000 rpm respectively. Calculate the number of stages of each impeller of a similar multi-stage pump to lift 5 meter cube of water per second to a height of 20,000 centimeter when rotating at 1,500 rpm. Find the diameter of each impeller of a similar multi-stage pump. The question is regarding a single stage pump and a multi-stage pump. We need to calculate the number of stages that is required for the particular set of flow conditions and required head conditions for the multi-stage pump. And in the second part of the problem, we have to determine the diameter of each impeller of a similar multi-stage pump. So we can try to solve this problem. So in this particular problem, there are two different sets of pumps. One is a single stage pump and the other one is a multi-stage pump. So there will be the single stage pump. The discharge is given as Q is equal to 3 meter cube per second. And then the manometric height is given as 30 meters. The diameter of the impeller T is given as 0.3 meters. Speed N is given as 2000 RPM. For the multi-stage pump, the discharge is given as 5 meter cube per second. We need to calculate the head, and then based on that head, we need to calculate the number of heads which is required, number of pumps which is required to raise the number of pumps which are required to raise the total fluid, the fluid to the total height which is present in this problem of 200 meters. This head per stage. And this is a series staging of the pump. Because of that, the flow rate remains the same. Head actually gets added up. So we require the head per stage, and based on this head per stage and the given head of 200 meters, we can calculate the number of stages. Diameter, we also do not know the diameter of the impeller in the case of the multi-stage pumps. And the speed is given as 1500 RPM. So these are a set of homogeneous homologous pumps. So for a set of homologous pumps, we can consider the equation of specific field. So the specific field is n root 2 divided by h power 3 by 4, same as n root 2 and h power 3 by 4 of the multi-stage single pump case. So this is the specific speed comparison. Here, n corresponds to, for the first case, n corresponds to 2000 RPM. Root Q corresponds to this. You need to remember one thing. This is not the dimensionless dimensionless form of the specific speed. This has got some dimensions. In order to include the dimensionless speed, you have to multiply h by g, g term. Then we will be getting the dimensionless variant of the specific speed. This will be 3. H is 30 power 3 by 4. Into 5. You need to calculate the h. Therefore, h based on this calculation, we'll be getting it to be 28.71 meters. And in order to calculate the number of stages, n is equal to h total divided by h. So h total is 200 meters divided by 28.71. So we'll be getting it around 6.96. So approximately 7. The number of stages required to lift the water to the overall height is 7. So 7 stages are required to of series combination of the pumps with the new features in order to deliver water to the required height of 200 meters. The second part of this question, we need to calculate the diameter of each impeller of a single stage pump. So we have what we have is that we have flow rates, we have the heads, we have the RPMs. So we need to try. We really need to try to bring an equivalence, which will be having components of all these four. Thereby, we can get the value of the diameters. So as per the second, we in the previous week's lectures, we have seen 5 different coefficients, and out of that, there is a second coefficient called the head coefficient. So the head coefficient takes a relationship between diameter, the RPM, as well as the head. So we try to bring, we use the dimensionless quantity head coefficient, get the value of diameter of the of a pump in the multi-stage phase. In that particular case, the what we can write is that head divided by RPM squared multiplied by the diameter squared of the single stage case is same as the same quantity for the multi-stage case. We know the value of the head for each individual units RPM. What we need to calculate is the diameter. So this is applicable for the cases of the pumps which satisfy all the similarities. Dimensional geometry, kinematic, as well as the dynamic similarity. So from this one, we can calculate the diameter D to ask the H value D, the RPM 2000, this diameter is 0.3, H here is 28.71. From the specific speed analysis, we have calculated the H value per stage, and then the RPM in this case is 1500, and we calculate the D2. So D2 will be coming around 0.391 meters. So that will be coming around 0.91 millimeters. So this is the answer. This particular analysis, we had unknowns diameter and head for the multi-stage pump, for an individual pump in the multi-stage case. We invoke the equation of the specific field, and we got the value of the head, which will be developed by an individual pump in the multi-stage case. Using that head and the available total head which need to be lifted, for which the fluid need to be lifted, we have calculated the number of stages required in the multi-stage pump. And since we have the head available right now, as well as the given problem, the problem given in this question has all the other parameters mentioned, we can calculate the diameter using this dimensionless variable of head coefficient. So the dimensionless head coefficient states that for the similar pumps, we can use this dimensionless quantity of this head coefficient, and that will remain a constant. So the dimensional quantity is h divided by n squared into d squared. Using this value, we can calculate the diameter of the individual pump in the multi-stage case. Any doubts? If we can look into the next problem. The actual velocity v of a particle depends upon the time t according to the below equation. What physical significance A and C represent mentioned in the question using the dimension analysis concept? What So in this particular problem, four options are given. A represents length, while C represents acceleration. A represents time, while B represents length. Both A and C represent length. A represents acceleration, while C represents time. So the answer to this problem is both A and C represents length. So in this particular problem, I forgot to add the equation in this problem. Take a pardon for this. This is the equation which I have missed in the first attempt. So the velocity left hand side and to make it a bit more clear, v is equal to root of AB plus dt plus c divided by d plus t. So in this particular unit, velocity unit is meter per second. The unit of b should also dt should also be meter per second. So correspondingly, that means that the unit of b should be meter per second squared. Correspondingly, the unit of a should be the unit of AB should be equal to meter squared per second square. A we know as meter per second square. So the unit of A will be meter. Similarly, the unit of C by D plus T should be equal to meter per second. The bottom unit will be second, and C unit will be meter. So both A and C represent length. This is a basic equation which this is a basic question which uses the dimensional similarity on the both the sides. Any questions based on the previous problem? Am I audible? Is the screen visible? Am I audible? Is the screen visible? Hello, am I audible? Am I audible? So we can move to the next problem. A reservoir has a head of 40 meters and a channel leading from the reservoir permits a flow rate of 34 meter cube per second. If the rotational speed of the rotor is 150 rpm, we have to calculate the dimensionless speed. In this particular problem, the dimensionless speed, dimensionless specific speed. So the unit of this quantity is for a this is the case of a turbine, not a pump. Fluid is coming, liquid is coming from a height. So for the dimensional specific speed quantity would be coming for the turbine as n root p divided by, instead of the discharge, it will be power n root p divided by density power half gh raised to 5 by 4. So in this particular problem, we have the n as 150 rpm. We do not know the power. We have the density, liquid, water. G we know, head is given as 40 meters. We need to calculate the power, and based on that we can calculate the specific speed. So power generated will be equal to OG into QH. Rho is 1000, 9.81. Q is the volume flow rate. It's 34 meter cube per second, and H is the head, 40. So based on this, we will get the value 13.34 into 10 power 6 watt. And substituting this power in the specific speed equation, we can calculate the specific speed n into ns is equal to 150 divided by 60 into root of 13.34 into 10 power 6 divided by rho half 1000 half into 9.81 into h head is equal to 40 meters power 5 by 4. So the value will be coming to be 1.6 0.165. So the value of the dimensionless specific speed based on this equation of entropy divided by density power half multiplied by jh the whole power 5 by 4. That is the equation for the dimensionless specific speed of a turbine. For a pump, we have to take into consideration the Q term and root 2 divided by x 3 by 4. But for the pump, for the turbine, we have to take in terms of power, and correspondingly the power, the degree, the power of the head term will also vary. It will become 5 by 4. So this quantity is equal to 0.165 revolution. The dimensional specific speed will be 0.165 revolution. So if you convert that into the radians, it will be 0.165 into 2 pi into 0.165 revolution. So it will be coming around 1.037 radius. Particular problem, we have determined the power, and based on the power, we have calculated the dimensional specificity. So the unit is entropy divided by rho power half into H raised to 5. That's straightforward problem. into the next problem. It's a problem which takes into account the air vessels which are present in the delivery side. We need to consider the pressure head in the cylinder at the beginning, middle, and the end of the delivery stroke by taking into account the buffering or the smoothing out of the pressure that will be as a result of the air vessels. So the question reads, the piston diameter and the stroke length of a single acting reciprocating pump are 20 centimeters and 35 centimeters respectively. The pump is running out. The pump is running at 40 RPM and delivers water to a tank 50 meters above the pump through a delivery pipe of 10 centimeters in diameter and 25 centimeters long. If a large air vessel is fitted on the delivery pipe at a distance of 1.5 meters from the center of the pump, find the pressure head in the cylinder and at the beginning, middle, and the end of the delivery pipe. Take atmospheric pressure as uh, we have to take the atmospheric pressure as 10.3 meters of water and IC friction factor of 0.03. Can see the question. In this particular problem, we'll write down the parameters which are given in this problem. We know the diameter of the piston in this particular problem. Diameter piston equal to 0.2 meters. The stroke length L equal to 0.35 meters. Speed of pump N equal to 40 RPM. The delivery head static height of the delivery tube for the discharge pipe is equal to 15 meters. Diameter of the delivery pipe equal to 0.1 meters. Length of the delivery pipe equal to 25 meters. We need to calculate the distance between air vessel and center of pump. In this particular problem, the distance between the air vessel and center of pump is given as 1.5 meters. Correspondingly, the length of delivery pipe beyond the pump, length of the delivery pipe beyond the air vessel will be 25 minus 1.5 meters is equal to 23.5 meters. So we can represent this to be LD dash and this to be equal to actual length of the delivery pipe. Atmospheric pressure head is given as the Darcy friction factor given as F equal to 0.03. We can calculate the area of the piston and also we can based on the stroke rate we can calculate the crank radius. L by 2. The total stroke length will be equal to 2 times the radius of the crank or the diameter of the crank circle. So we can calculate it to be equal to 175 meters. So we can calculate the area of piston, cross-section area of the piston as 5 by 4 into d squared equal to 5 by 4 into 0.2 squared equal to 0.0314. Area of delivery pipe is given by AD is equal to 5 by 4 into DD squared equal to 5 by 4 into 0.1 square equal to 0.00785 meters square. So we have calculated the piston area and the delivery pipe area. This becomes crucial to calculate the velocity in the delivery pipe. Similarly, angular speed is given as the RPM is given as 40. So we can calculate the angular speed 2 pi n by 60. So it will be coming around 2 pi into 40 divided by 60. It's somewhere around 4.181 or 4.189 radian per second. And these sets of information is really required to determine the actual pressure at the suction at the delivery stroke beginning, end, as well as the middle. The formula for the pressure head in the cylinder at the beginning of delivery stroke given by H is equal to H ATM plus the head associated with the static head term HT plus the pressure which will be applied by the amount of liquid that will be present, or the pressure which is needed to be applied on the air column, uh, that much also will be required in that will also be compensated in this head. So it will be corresponding to this particular quantity will take into consideration the inertial effects. So this is the acceleration quantity. A area corresponds to the area of the piston that multiplied by the acceleration of the piston divided by the area of the delivery tube that will be giving you the acceleration inside the delivery tube that multiplied by LD by J. This will effectively give you the pressure that is due to the head that is due to the inertial term that will be accounted in the water column. That will be accounted in the air column. And similarly, there will be a frictional head loss that will be taking the velocity and finally there will be an additional quantity that will take into consideration the minor losses. So that will be velocity of the discharge pipe. So that will be equal to A area into R omega divided by particular quantity. Based on this analysis, what we can write is that the HATM is 10.3 head term. The head actual term will be equal to 2. The inertial head term that will be compensated in the air vessel term, that will be equal to LT divided by G into A divided by AD into R omega squared. So LD corresponds to 1.5. That is the height of the air vessel from the piston center divided by 9.81. Area corresponds to area of the piston corresponds to 0.0314. Discharge delivery tube area is equal to 0.00785 multiplied by R omega squared. R value is 0.175, that is the crank radius, multiplied by omega squared. Omega in this particular problem we can calculate as 4.189 squared. Similarly, for the getting the velocity, it is r omega divided by phi. So this velocity term, velocity is given as 2 pi n divided by 60. Omega angular velocity is given as 2 pi n by 60. Therefore, n can be written as 60 omega divided by 2 pi. The volume is volume. And the delivery volume flow rate can be written as area of the piston into length of the stroke multiplied by n. That divided by 60 multiplied by the cross-sectional area. So in this particular problem, this n can be written as 60 omega divided by 2 pi. So 60 and 60 gets cancelled. So we'll get omega divided by 2 pi. And in this particular problem, the length of the suction stroke can be written as 2 times the crank radius multiplied by 60. Divided by 60. So n, substitute the value of n. So 2r divided by 60 multiplied by 60 omega divided by 2 pi. So cancelling out each other, we will get r omega divided by pi. So that will be the velocity associated with the distance. So in order to calculate the velocity of the distance delivery tube, we multiply it by a into r omega divided by ad into pi term, invoking the continuity equation. Similarly, for using for the friction head loss, it will be 0.03 multiplied by the length of the delivery pipe, that will be equal to 25 divided by 0.1 into 2 into 9.81. So diameter of the delivery tube is 0.1. Area will be equal to 0.0314, 0.0085 multiplied by 4.189 multiplied by 0.175 divided by 5. This 4.189 we have calculated. That is the omega value. 0.175 will be the radius of the radius of the crank pi term that is given from this equation on the right hand side, multiplied by the whole square plus area into r omega divided by ad into pi. So in this particular problem, the same thing repeats. So it will be 0.0314 multiplied by 4.189 into 0.175 divided by 0.00785 multiplied by pi, the whole square divided by 2.9.85. So this, simplifying this, we'll get the value of the pressure head in the cylinder at the beginning of the delivery stroke equal to 10.3. This will be 10.3 plus 15. This quantity will be equal to 1.878. That is the head due to the head which will be stored in the air column at the beginning of the delivery stroke. 1.878 plus 0.333 will be the frictional head loss plus an additional term of 0.044 taking into account the minor losses. The value will be coming around 27.55 meter of water absolute. So that will be the head pressure head in the cylinder at the beginning of the delivery. At the middle of the delivery, There's a slight tweak in the formula in the middle of the delivery. The pressure head in the cylinder at the middle of the will be giving you the velocity term of the piston. For the case of pressure head in the cylinder, at the mid-stroke, the X will be given as the atmospheric head plus the delivery pipe head plus the friction head losses. But at the getting point, the inertial effects will come to be zero. It will change the direction from acceleration to the deceleration. The velocity will be maximum at the mid stroke, and correspondingly the inertial term will be zero, and there will not be any inertial forces, inertial pressure losses, inertial head that will be opposing or supporting the motion. So this particular term will not be present at the mid stroke, and then there will be the frictional pressure losses in the entire stream, in the entire delivery tube, as well as the part of the section that is in the air vessel. So this will be the total FLD multiplied by DD into 2G. That will be giving you that frictional head loss in the frictional head. So that is in the delivery tube. That will be AD into omega R divided by pi the whole square. Omega R divided by pi, that will be the velocity of the piston plus the additional term that will come into picture in this case is the air vessel term. So that will be FLD, the length of the air vessel, the the frictional head losses in the supporting tube, plus the additional term that will come into picture, the minor losses. Substituting these values, will get the head loss term is equal to 25.874 meters of water absolute. And the final part of this question is the pressure head in the cylinder at the end of delivery stroke. Head loss will be given as H ATM plus H delivery 5 difference, and the corresponding discharge, which will be opposing this head, which will be in a which will be opposing the flow direction. That will be minus of that is coming from the air vessel term to compensate for the deceleration as well as the negative pressure that might occur at the end of the delivery stroke. So that will be minus of LD dash divided by G into A divided by AD into omega squared R. This is the uh, inertial head that will take into account the head loss. That will take into account the flow which is happening in the opposite direction. That will be and the additional head flow term that will take into account the whole delivery tube length multiplied by the corresponding velocity in the delivery pipe and the additional minor loss terms. We will be getting the results. Yes. This one, two, two, three, three. So solution sum of 0.044. That is that's a constant that takes into account the velocity. Velocity to the velocity. Therefore, total absolute. So in this particular problem, we have taken three different cases of the pressure heads at the beginning, middle, and the end of the delivery flow. The only difference that takes into account between the middle and the that takes into consideration the head due to the presence of air vessel. That will be trying to smoothen out the difference in the pressure. So if the actual head that should be developed that takes into account a portion of the actual head will be stored in the air column just above the uh, water in the air chamber. Similarly, the same energy is stored will be released at the end of the delivery stroke to take into to compensate for the deceleration and additional inertial losses. And at the middle stroke, and since the velocity is zero, velocity is maximum, the pressure, the initial head acting on the fluid will be zero, but correspondingly there will be, since the velocity is maximum, there will be an additional head losses to take into account the amount of flow that is happening in the air channel. So these three considerations result in the results in three different head values at the beginning, middle stroke, as well as the end of the delivery stroke. So the pressure will be maximum at the beginning of the delivery stroke. Mid stroke, it will be an average value. At the end, it will be very less. So that completes the problems for this session. We have seen a few multiple choice questions and a numerical answer type questions based on water columns, based on the air columns, air chambers in the positive displacement terms. We have seen a few questions based on the dimensional analysis, specific speed, and Buckingham's pi theorem. So in the next week, we will start the discussion on the turbines and the different types of turbines and the degree of reactions that can happen in the turbine. So that's all for this week. Have a good week. Bye for this week.